Okay, thank you to be here for this lecture. And let me restart from the last slide of the previous lecture, in which you can see here, I summarized the basic 5 equations. I tried last time very quickly to explain the meaning. It could be that I will come back a little bit later. I would like just to recap. And nevertheless, I would like to show you very quickly how this expression, which is everything is important, but basically this is the result, I will repeat again, the result of some boring calculations, which I have the book here. I have the book here to show you why I didn't put in the slide these calculations, because really the calculations don't encourage you to remain on the course. Equation number 1 and equation number 3 came from very boring calculation, not difficult, but absolutely boring. In any case, look, we have, do you remember, 2 steps in the structure of the Kalman field. We have the state prediction with 2 equations, which we have the estimation system state, which, you remember, I insisted a lot about the concept that we have here minus, and we don't have, let me close here. We have here minus on the left part, and we don't have a minus here. And this is a very important difference, because what we have on the left part, the natural, what we have on the left part, is not the same what we have on the right part, even though both have hat. The reason is, as you remember the lecture last time, that on the right part, we have the corrected variable, or the state variable, or the state vector, you can call as you want, which came from the previous step. The previous step can be considered the correction step. The question number 2 is, let me say, the prediction of the error, roughly speaking, you remember, but in form for the covariance matrix, error covariance matrix. You remember, so here I sketched the boring calculation. Very important to notice also here, something, if you look on the left and the right part, came from the correction, because we have a minus here and we don't have a minus here. And the preview, let me say, output, better to say output, because the correction is the second step inside the sample time. Do you remember? Inside or within the sample time, we have 2 steps. When I speak here about step, we have to be careful. Probably I have to be more precise, because K-1 is referred to the previous output of the Kalman field. Everything to start with the state prediction at the beginning of the algorithm needs, the state prediction needs at the beginning, exactly when I started. We will see now with the software, the initial vector of the variable which I want to estimate, and also the error, let me say, the error P. Is the covariance, I told you, a little bit more complex. We will see with MATLAB a little bit more in depth. But after the first step, why is let me see what I can do to improve this connection. After the first step, we can see the recursivity of the algorithm, because x hat k-1, let me say, the current step equals, or let me say, excuse me, the previous step, k-1 is the previous step, is the current step. I mean, the output which we have becomes equals the current step, in order to loop again. We will see with MATLAB this concept here. It seems to be a little bit complex, but this means that the output which I have after the correction is the value for the next step, the next loop. Let me show you one thing of how I can calculate this KK, because you remember last time I told you that the KK and PK came from an optimization problem. And now I will show you what I intend with this optimization problem. Look, do you remember this? I told you that the optimization problem is defined through this equation here, basically the derivative of the trace of the a posteriori error covariance matrix with respect to KK. This means equals 0. This means I'm looking for the minimal value of this trace with respect to KK. What is the trace of a matrix? PK is the matrix. But think about just one scalar. If you think about just a variable, I show you with the example now. This means that we're looking for the minimum of PK as a function of K. Why PK is a function of K? We can see from here, because PK is defined as the expected value of this product here. Think about Mascara at this moment. No, here in Bachelor, we are not so happy to work with matrices. Basically, the error squared, a posteriori error squared. Basically, the error related to the correction. You remember, this is the error related to the correction. Very important to notice that why everything depends of K, because X hat K depend of K. You can see here. This is the hypothesis of Kalman, which he says, I would like to find the correction, the a posteriori, let me say correction, or the corrections as a sum of the a priori estimation plus this concept here, KK, which multiply this innovation. Do you remember I told you last time? But we can see that everything depends of K or KK, because I can consider K which changes over time. Now, the trace is the sum of the errors. But of course, the idea is to be sure that not only the sum of the error, but each error is minimal. In linear case, it is. There is a theorem which we can demonstrate that all these errors, do you remember the example which I told you? We had two errors, current error and velocity error. They are orthogonal. This means if I minimize the sum, I necessarily minimize each error. This is a little bit difficult in the theory, but believe me at this moment. If the hypothesis, which I told you last time, let me say, hold. The problem is convex. What is the meaning of convex? You have something to write for me? No, you don't have. Let me find something to write, because I would like to explain what is the meaning of the convex optimization problem. One second. You know, not only control system, no? I told you. Let me see what I can. You don't have nothing to write, no? I'm just hoping that this is very anything. Okay, doesn't matter. Let me see. You don't have anything, no? No, no, no. Sometimes you have some difficulties to. Let me see if I find something here. Okay, let me see here. It's a shame I cannot upload this material, but nevertheless, we can go ahead with the lecture. Okay. Let me try. It's a shame I'm not so well organized. I told you that we are in the presence of, excuse me for this improvisation, but I told you that we are in the presence of a convex optimization problem. What is the meaning of this? If all hypotheses which I told you last time are satisfied about this, let me see if I have already something prepared, because sometimes I have it here. Let me look. No, partially. I will also later something to show you. Look, I don't know if it's visible. Probably no, not yet. Hmm? An optimization problem. We say that an optimization problem is convex. If you have just one minimum, in this case, we are looking for the minimum, because we want to minimize the covariance matrix. If the hypothesis of the Kalman is satisfied, we have something basically have something like that. We have a positive function because it's the error square. Let me roughly speaking the error square. Of course, the situation is a little bit more complicated because we have a matrix, but let me go ahead slowly. And it doesn't matter where I start. You can believe me intuitively that if the algorithm is well conceived, I will fall down here. Let me explain really roughly speaking. Therefore, we can now justify exactly what I told you before. Exactly this, because if you remember, excuse me, if you remember in gymnasium, uh, if we know that the function is convex, roughly speaking, from your knowledge in gymnasium, it is enough. This condition is also is not only, excuse me, necessary, but also enough. I don't know if you remember from gymnasium that the derivative of a function equals 0 in general is necessary condition, but not enough. You remember we have to check for the second derivative, third derivative, and so on to say is maximum and the minimum or a subtle point and so on. But if we know that we are in the presence of an convex function, or at least locally convex if you are in the Nakamura topos. Of course, like here, here we have something more because in the hypothesis of Kalman, it seems to be that is globally convex. Therefore, I told you it doesn't matter where I start. Do you remember I told you that the Kalman algorithm needs to be started with what? With initial condition of x hat and initial condition of p. Here it seems to be that they correspond. But in the reality, here, because I know exactly in the sense p. But in general, of course, I can put to start the algorithm x here, x at 0, and I can put here p0, which does not correspond to px hat 0 because God knows where I am at the beginning. But nevertheless, the algorithm will be able to solve this mismatch. We will see together what I intend. Now, let me conclude with the slide, and let me open the next slide, which we will see very shortly, the example which I want to consider, and then directly with MATLAB. I try to introduce also MATLAB. I know for somebody it's very boring, but here we have for everybody. The course is for everybody. Therefore, we are in complementary study. This means to be patient. No, in the sense of a good question. Thank you for this question. You have to know what concept. It is enough to know, as I told you before, just one language to understand all possible languages. The reason is we have many similarity, but it's my sentence. I don't want to justify this sentence considering the similarity. I want to justify this sentence considering the concept of the program. When we have in mind what is we have a feeling about what is the meaning to build the program, the meaning of functions, the meaning of if loop, subroutines. These elements are present in all languages. This means it could be that instead of comma, this tool or that this platform needs semicolon. It could be that the function is built with another structure. But the concept of the function, the concept of subroutines, the concept of global variable, we will see together, it's similar. In MATLAB, we have another advantage. We will use also Simulink together. We combine Simulink MATLAB. Simulink is MATLAB. Is subroutine is a graphical representation of based on MATLAB. This means each block of Simulink calls function in MATLAB. But this graphical structure helps us. It's more friendly than other languages, in my opinion. It's more powerful. This means somehow I would like to say, I don't want to say it is easy because it somehow is easy, but we consider more difficult problems. This means at the end, yeah, it's difficult. But if you have in mind what the programming is, you will not be surprised what I will do it. Okay, let me conclude here. Do you remember last time I told you that, but I already repeated here, the meaning of matrices Q and R. We will see now in depth with the simulations. Do you remember I told you the Q and R as matrices which we cannot do, which cannot know perfectly. The uncertainties, if they are uncertainties, of course, we cannot do perfectly, know perfectly, but we can use this to tune the kernel filter. Okay, but to tune means I have to know something in advance, or I have to be able to approximate this value Q and R. This is the tuning. And very often we are using different algorithms. For instance, PSO. Shana, remember? You know PSO, do you remember? They are meta-heuristic algorithm based on, let me see, algorithm with artificial intelligence, or the based on artificial intelligence and so on. We can use also neural networks from the data to be able to estimate this Q and R, which we need to obtain the optimal value of the estimation. But I would like to emphasize this concept here. Let me come back here. Q and R, in the case of which I am explaining now, linear case with the hypothesis which I told you about the noise. If you look at the lecture, you remember Gaussian, white noise, linear system as dynamical system is not necessarily to achieve this point. I will achieve nevertheless this point here. But the problem is we will achieve with a transient which is not optimal. I mean, exists just one R, value of the matrices, just one Q, value of the matrix. We will see now in a value, which achieve this point is an optimal way. This means we have a transient, understand what I will show you with the simulation, which is not optimal. But we will nevertheless achieve the goal. And when we achieve the goal, then the steady state will be optimal. This means, of course, very often we need a supplementary software to estimate Q and R. I will repeat everything because I know this is a little bit difficult. Using the software, we will go in depth and a little bit on this convexity and not convexity when we will try I will try to explain the extended Kalman filter, in which we will see that the problem is not convex. This means we have more than one minimum. Let me open the second, another presentation, which is in my study, in order to introduce, before opening MATLAB, opening, MATLAB, I will introduce the case. You can find this is in the folder of today. Let me open and let me share. 1 second, I need. Now we have a problem with the connection. Yeah, I hope that. No, I see now the folder. 1 second. Did you see the folder of today? 25, 26, I don't see it. Yeah. Okay. The lecture looks like, let me open the lecture, the presentation, or the file, and the PDF file. Let me share now. We can see also this one is an old file because, as I told you, we are using basic knowledge already established in the course. Okay, let me see this example. I will present a few words, and then we will move to MATLAB. As is written here, before reconsidering the DC driver, do you remember drive? Do you remember I told you that basically the course was conceived for engineers, therefore these electrical systems. But we will see that we can consider a very abstract system or elements in our course. Think about this kind of problem. To estimate a constant, R recall as the resistance. Why that? Because we will see later when I try to reconsider DC motor or DC drive, we will apply it again this. It's in a particular constant because it seems to be if you read this expression here, somehow I put T is not wrong. It's in a constant, yes, because the derivative of this is 0. You remember in gymnasium, if the derivative of a function is 0, this means this is in a constant. You remember this? from Gymnasium. Now, nevertheless, I put as a function of t. It's not wrong, because a constant is also a function of t, but it's constant. Does not change over time. So formally, it's not wrong, but I can avoid to put t because it's R for each t. Why, nevertheless, I put t? This is an important concept, because in the Kalman filter, or at least our problem, which we want to define inside the Kalman filter, is to estimate as a constant, which I don't know the number. This means we have to give the possibility to Kalman to estimate this variable. Do you remember we have seen before that starting from an initial value, the Kalman filter try to estimate, to move from this initial value, let me say, to the true value in the sense of Kalman. Let me coming back on this. This is important. Excuse me. Today, Shanna, do you have something to write for me? No, you don't have. Ah, okay. The engineers know that we have to. No, I need this. I have a piece of paper I need. Oh, no, don't destroy it. No, don't destroy this. Okay, I write it in your. I can write everywhere. Okay. I try to explain this concept, which is fundamental. Huh? Again, this picture, or this graph. Yeah. Ah, better.
And you can use this one as.
Oh, but yeah. Again, as before. The particular x hat, which minimize here. To be correct, I have to write, you remember, p of x minus x hat, to be exactly correct. But let me write in this form here. But if you want, should be better. This is exact something better as before. As I told you, I will start with an initial value. See, I intend. In our case, this is just one value. It depends on the error. Of course, we can see that this value here, which is my constant to be estimated, because minimize the error between my, let me say, initial value and my final value, but I need time. I mean, I will estimate R, minimizing the estimation error, but I need time. This means make a little bit sense now, the more sense, this formal aspect, to say that R depends of T. Because at the end will be 0. But before I estimated exactly the value, we will change. We will see now in the simulation. Starting from an R0, which basically, let me say, I don't know, but assuming that this is not yet, let me say, is not yet the Kalman. No? It's not yet the Kalman. I don't know if I have it. I don't have it here. I will come back on the slide now, on the lateral camera. Here is not yet Kalman because, do you remember, I don't have here hat. minus and not minus is not discrete. It's just a model. It's just a model. But I anticipate what I intend, introducing why I emphasize this T. This is the model, which assuming that here I know exactly the initial value, or the initial value equals the final value. This is the model. Look, if I realize the discretization of this, we have this system here. I don't know if it's clear, because the discretization of this here is R of k minus R of k minus 1 divided Ts sample time equals 0. Do you remember this? I show you here with the lateral camera. Starting from this model, formally, I try to explain why I emphasize with the presence of T. Everything is correct. This is the model, in which assuming that at time 0 I know perfectly the value. In this sense, I don't need Kalman filter, because if I know perfectly the value, the nominal value, I don't need Kalman filter. Now, let me realize the discretization of this system here. Is it a dynamical system? Formally, yes, no? Because we have the derivative. The state of the system is R, very important. The state of the system is R. How I can represent this system here? In discrete form. You remember, I invested time to introduce R nominal means the value, no? R nominal means 10 ohm or 10. Don't think about the resistance. Now, from here, we have this Rk equals R of k minus 1 for each k. For each k, no? K is starting from 0, no? From 1, excuse me. This is from here, I will obtain this. This is basically the concept I express. What is this expression? Say that k, excuse me, R remains constant. Because if for each k, Rk equal Rk minus 1, it's clear from here to here, no? Math. This means R is constant. But, of course, in the Kalman filter, if you remember what I told you last time, also today, this is the prediction model in which we have, you remember, a minus here, and then we have to put hat because it's the approximation. We have a hat here. But if you remember, I put also the matrix, in this case is not a matrix, the value Q, which is basically the error variance in this case, because we have just one state. We cannot speak about the covariance because we have just one state, which states that this equation is not perfectly correct. The variance means we have a variation. Think about the gymnasium. Why we have a variation? For different reasons. It could be, as basically happens, that the final value, R nominal, is not known directly from the beginning. You remember this concept here. At the beginning, at time initial value, at time 0, initial value in it. Put 0 if you want. You know? We have a difference. This means, of course, we have a differences, an initial error. This initial error, nevertheless, is not in Q, but in P0. Do you remember this? This means we have nevertheless in P0, which is present in the prediction error. We will see now with the MATLAB. The error which we have here at this moment is the error in the discretization, because the exact model is this one. This is a discretized model. This means here, nevertheless, we have a variance between the discrete model, excuse me, and the, let me say, ideal model. Moreover, because of this difference, we have an error at the beginning in P. Do you remember? I told you exactly with the last slide of last time, I repeat it today. P0. If you want, I can back in the lecture again. And this must be considered in the Kalman filter. Let me show you the Kalman filter using now MATLAB. If you look at the lecture, I copied the code in the lecture, but I would like to show you directly MATLAB. So in any case, it's the same. Let me consider again, nevertheless, the lecture which I have seen before in order to show you again the concept of the P0, which of course is an estimation. Let me look. It's the lecture of last time. I show you again the lecture of last time. Now I would like to show you again one slide of the lecture of last time. In MATLAB, yeah, MATLAB is there. 2 files, you can find 2 files. I hope it's correct what I upload. Let me show you. Because I have so many files that sometimes I can mix, but I think it's correct. Let me share. I show you what I intend. Again, yeah. This Q here characterizes the error. It's exactly what I told you before, is the error between the ideal model and the discretized model today. The error which we have in this constant is just the error due to the discretization, because it's not exactly the physical model. The physical model is a continuous model. What I am telling you about the initial error is exactly here. I have a value which is not the nominal one, because no, God knows the nominal one. This means I have to estimate this. I have to say what I think what is the truth. And of course, I have to, in order to start, I have to also say that the Kalman filter, what is the error? The variance of the error, to be precise. Let me say, roughly speaking, the error. Let me see if I am able to. Yeah, and these 2 values are enough to start. But independently where I wrote here, I will nevertheless achieve the goal, because the problem is convex, the optimization problem. I told you a little bit about the convexity. But of course, I will achieve the goal, but not in optimal way. The transient is not optimal. Let me open MATLAB. I will repeat the concept of the transient. I will repeat everything again. Okay, please open MATLAB. If you want to open MATLAB. If you don't want, it does not matter now, because it's enough if you follow me. If you follow me here. To I think no. Let me open MATLAB. To open MATLAB, it's enough that you click twice on the icon. If you need, as I told you last time, to access access to the MATLAB, send me an email. I will forward you with the data ID, family name, your name. I will forward the data to the technician. It works. But the problem is from home. I don't know if you are able to work without an code or something like that. Did you try it? From home, yeah, I intend. From here, yes. Try to do at home. It could be, you don't need here any code, any password, I think. I don't know, because I am working with the local version of MATLAB. I never use from home for two reasons. I have a local version, or the versions, I have more than one. And most of the time I'm at the university. This means I don't understand why I'm not able to open the file now. Okay, let me see why is this. I'm not able to open this. Ah. Okay, let me click again. Should work. Oh, okay, now it's working. Excuse me again for this inconvenient, but I'm now it is opening. And let me show you directly MATLAB quickly, the idea, but I will repeat again many times the structure of MATLAB. MATLAB is a really huge program, but believe me, it worthwhile to come here just for MATLAB. I told you last time, because MathWorld organizes courses of MATLAB, also basic course of MATLAB. It costs 1,000 euros per day. It means just to learn MATLAB, it makes sense to come here. Of course, the course is organized in different forms. Of course, more effective of this it could be. But I remember when I attended the course, it was not a basic course. It was an advanced course connected with microcontrollers and so on. After 2 hours, after the first 2 hours, I was not able to understand anything, because too many information, too many. At the end of the day, just in a feeling, but okay, let me share MATLAB now. Now, where is MATLAB? Now I see it. Let me share. Today I have just the time to present this example here, but this does not matter, because I would like accelerate the velocity of the lecture, let me say, later, because at the beginning, yeah, it's a little bit difficult for you probably. Okay, let me explain very quickly what you am. Do you have this interface? No? Do you have this interface? What we see together very quickly, and then, because at least I would like to finish with this example. Yeah, it seems to be complicated, but it's not. Look, here we have something which is familiar. Because in this version here, which is the Windows version, we have here the path where we are. This means we are in the F, which is my memory stick or something like that. And then we are under the folder named lecture _ WS and so on. And the subfolder Kalman course, and again, the subfolder called lecture 1 and so on. Clear. This is the Windows structure. Look, on the right part, let me say on the right part, we have the files which are present in this subfolder here. In my case, of course. In your case, you have to put the file, which we will see together in a few minutes, in one folder or a subfolder. This is known from Windows. Windows is known. Everybody know Windows a little bit, no? Also in the whole background of Windows is known. And here we have files, we can see here, which are characterized by different extension. We will see immediately the .m. M indicate the family, MATLAB. The meaning of the word MATLAB is matrices laboratory. Therefore, until now, we have seen matrices. I'm speaking about matrices, or the matrix, singular. And then we have the extension SLX Simulink. In the past version, we had MDL and the Simulink context model. Look, command window. Here, we can use this part here in a very easy way. For instance, 1 + 1. The answer is 2. Answer equals 2. We know that 1 + 1 equals 2. This means we can use this part of this interface to calculate, but we can use also to put some comments. We will see together. Now, very interesting, on the right part, workspace. In the part of workspace, we have all possible variables which are active, let me say, in the kernel of the program. We can see that we have here active A and S answer with the value 2. But of course, if I write answer 2 equals 1 + 2, we can see that the answer 2 equals 3. And we have here on the right part in the workspace 2 variables which are active. Answer with its value 2 and answer 2 with its value 3. We will see later a little bit more in depth. More interesting is the central part here with .m. Look at this PSO algorithm. We can write very complex software. Very complex for, we can see here. We can see minimum. We can see vector while. We can see for again. I don't want to tell you now about that. We can see if loop and so on. We can really realize the program in this part. We can use, nevertheless, this part here as a data file, as is the case, which I will present now. Let me open now the M file, which you can find in my study. We have just one M file. You can see that we have an SLX file, if I remember well, and M file. Yeah. I hope no mistakes in my uploading files. Let me show you. Because today, every day I'm confused, but today in particular way. Let me look. Oh, stupid. Oh, no, okay, I'm able to. Look, looks like the M function. Excuse me, I made mistakes. In this case, I don't need a data file. Excuse me. This is directly in a function, more interesting. This is directly in a function. I mean, as M file, and the M files can have many tasks. Could be a data file, is not our case because it's extremely easy. We have seen, I think, in a data file, and not in this course. In this course, this is the first time which I present MATLAB. Yeah, it's the first time. Now, the M file in this case is exactly a function. Do you remember? I told you that we need functions. Look, it seems to be that this function is defined using the command function. After command function, I will define an output. This is equal name of the function with the argument. The argument could be vectors, could be more than one vectors, but could be also in a scalar, as in this case. Why in a scalar in this case? Because we have to estimate R. X equal R. We will see later in a few minutes in combination with Simulink. Here it seems to be that X came from another structure because a function is something which must be called. I don't know if this, you know, in R, which must be called. The function must be called also in R. This means we will see where X come from. I will define the global TS. Global means that this variable should be read from everywhere. Not only inside this function here. Function is basically a subroutine. It's in a sub-program. I don't know if you in R is know what is in a sub-program. I'll show you here. It's in a sub-program. We will see what is the main program. It's in a Simulink file. The main program in a Simulink file. We have here the input at the step 1, but I told you we don't have input at the step 1 because the model is R of k equals R of k minus 1. We don't have input because we have just the state. The second element of X is the output. We will see that nevertheless, formally here, we will see that this X really is in a vector. Really is in a vector. It's not exactly in a scalar, as I told you before. But nevertheless, is in a vector which describe R, and it's let me say possible aspect of R. X3 is the old value of the R. A equals 0, B equals 0, because as I told you, we don't have inputs. I mean, I can put whatever value of B because we will see that U8 is 0 in our case. Or I can directly say B equals 0. Why A equals 0? A is equal 0 because the real model, let me show you. The A matrix is 0 here. We can see here A0 multiply A plus B multiply U. It's extremely trivial, the real model. A multiply 0, or excuse me, 0 multiply R. This means A equals 0. Probably I told you something wrong, but 0 multiply R plus 0 multiply U. The state is R because the derivative of R is present in the model. Once clarify the continuous model, I don't know if you remember, I told you how we can calculate. Really, I told you this. The corresponding discretization. If A is given and B is given. Otherwise, look, you can write here is written, even though it's commented, because after the percentual, everything is commented. We can see the green color here. No? The green color means no active meaning, everything which is in green color, because it's after this symbol. This means command. I comment this as a comment. This means error of k equal of error of k minus 1. Instead of this line, you can activate 23, because 23 says error of k equal error of k minus 1, because xa is the past value. Resistance, if I consider resistance as a state, but old value. After that, I am able to start, because at the position x, we have the initial error. I can suppose what is the initial error, or have to estimate with some preliminary test. I am measuring R. W and Qx are exactly our covariance or the variance in our case. We will see how change the results if I have a difference value of Rw and Qx. Here I put again AD, the discretization. Probably it's the first time where I put, yeah. I need AD because I don't know if you remember the equation B, which I presented last time, must be present in the Kalman filter. You remember the discretized matrix transpose, multiply PA, the a posteriori, in this case, variance, error variance, which nevertheless change at each step. We will see in a little bit in 1 second when I open the Simulink. And then look, these 3 elements define the Kalman gain. KK, do you remember the results of my calculation? I forgot to show you the calculation, but I show you now at the end. Here is just in the position. I don't need to do this because we have just one element in Kn, because we are measuring just one variable, R, or the constant. Here is the a posteriori estimation, the result of our kernel. And here the new, the calculated a posteriori estimation for the next step. Here's the output in the context of MATLAB. Of course, what I am using now, we will see, is not so modern software, because we will show you that I am using an interpreted Simulink structure. But I think didactically at the beginning, we will see later more different Simulink structure, which is embedded. But I think this way to proceed is a little bit easier in the context of, let me say, I would like to say didactically. Let me show you what I intend. If you open the other file you can find in my study, this file in the Simulink file, which looks like something like that. We need time to open, but I think we will open, I hope. Why is so slow now? It's coming. It's coming. It's relatively slow because, second. Okay, let me show you. This is the main file. In the context, let me. In the context of Simulink, isn't a matter file, of course, because each block calls an M file. And here we will see now the connection with the function which I tried to explain. Next week, I will restart with the explanation, because at the beginning, it's extremely complex for somebody in any case. We can see here, and the block, we can see estimated R, Kalman gain. We can see here something which I am measuring. Let me go here inside. We can see that here we go inside with U, which don't have input, as you can see from here. We don't have U, because I told you exactly that the model doesn't have an input. We have a measure data, which is exactly what I am measuring as a variable. And here is a little bit complex, but you can see here an interpretive MATLAB. And here inside, we have the name of the variable of the function which you have. Do you remember it? Constant est, excuse me. Constant estimated. Let me show you also at home. In order to understand. Let me come back. Look here. This element here is our x, which is in a vector, which allows basically to characterize the variable R and some aspect of the variable R. It's not exactly a scalar, as I told you at the beginning. In this case, the scalar is R, but I need some elements of R. We can see which one. R, which I measure. The past R, we can see in a delay block, which you can find in Simulink. I told you next time where you can find this block. The past P, we can see here. You remember, to start, we need initial value of P, which you can find here inside. One, assuming that I estimate one as initial error, covariance error. We say error just to say roughly. And also here inside, we can see that we have also one. Excuse me, I made mistakes. If you look here inside, I think it's here, no? Yeah. Yeah, also here, the initial value, what? Could be also a different. Now I show you a different value. Okay. I will repeat also next week, but let me show you something more practical now. What is the problem? Assuming that the real value is 100, but I put 1 because I don't know what is the real value. You remember in my scheme, we have, I'll show you what I intend. We have this value here, which just God knows what it is, 100. The initial value is 1. I mean, here is 1. Look here. Here is 1, the initial value. And the true value is 100. The Kalman filter should estimate 100. The problem which Kalman filter has is not only a wrong, let me say, initial condition, but also in a wrong variance, because the variance between 1 and 100 is not 1. It's much more. If you remember in statistics, huh? Yeah, it's the difference, no? It's the root, remember that, between 100 is 1, 99 root. This means I make both mistakes. Not only, Kalman filter notice difficulties, that the measurement is wrong. Look, here we don't have just 100. We have 100 plus, let me say, plus a Gaussian error. Here I put a random number with Gaussian distribution, white Gaussian distribution, in order to respect the hypothesis. If this is not respected, we have a different form of Kalman filters, or we have to approximate somehow. I will come back on this. I don't have time to tell you a different form of Kalman filter. Let me show you the results. Everything is wrong, 1 minute. Then next week we repeat this. We remain on it. This is a fundamental example. Also, first time, MATLAB, Kalman is extremely complex. Let me show you the results. I am starting from 1. I put the variance totally wrong. And I am measuring not 100, something different. Let me compare here. I will tell you about where you can find this element and so on. Look. Excuse me, I have to initialize the value. Excuse me, I have to initialize because otherwise I have mistakes. I tell you next time what I will do. I have to write global TS, and I have to define TS. I don't know in this case until like that. Now should work. 1 second, just I show you just now should work. The results. And next time we will go in depth on this. Look, despite these uncertainties, noise, error, I don't know, should work. Noise, uncertainties in the initial conditions, uncertainties in both initial conditions. Initial value is covariance, but the variance in this case. It takes time, but it seems to be working. Oh, errors, let me see. Because I am not in the folder. Let me see where I am. Yeah, let me go in the right folder. Do you see? Yeah. Also, this you have to select the right folder where the file are. No? You generate one folder for you. No, yes, it's running. Look. Just really a few seconds. Look what happens. And then we will discuss next week how interesting we can see that despite the initial error, in fact, we can see that I start from 1 very far away. Let me see if I'm able to show you. Believe me, we are starting from 1 somewhere. The ideal of the nominal value is 100, do you remember? I am measuring yellow, wrong value. Nevertheless, we can see that the Kalman filter slowly, but we will not excessively slowly, we can see here. No? We will discuss how fast can be estimated using P0, Q, and R, but we can see how Kalman filter is working. Many uncertainties in the measurement, yellow instead of red, initial error in the error and the initial value. Independently of the initial value, I will reach always this, but of course, more or less, faster or slower, depending on many things. Okay, let me close. And if you have question, I can answer you the question. Next week, I will repeat again. Don't let me say, give me a little bit time, because I understand that everything is new, bachelor complementary courses. But if you have question, I am here for to answer your question. Otherwise, now we will see next week with the repetition of this. We will go ahead a little bit. Thank you for attending this class.